Hello and welcome to the very first episode of Delving into Academics. It's a podcast where various researchers from biology, chemistry and physics are interviewed about what they're currently working on and their life as an academic. Our very first episode is with Victoria, where she discusses working with CERN and her work in particle physics. I hope you enjoy. Today I'm here with Professor Victoria Martin. She has a background of mathematical physics here at the University of Edinburgh for a Bachelor of Science. She graduated in 1996 and then went on to do postgraduate at the University of Edinburgh again, working on CP violation. She completed this in 2000 and then went on to do postdoc for 5 years at Northwestern University. She then returned to become a lecturer at the University of Edinburgh in 2005, and from there she's working with the ATLAS experiment at CERN in Geneva and at the Compact Linear Collider. Thank you for coming on the show.
It's great, Jessie. I think this is a great idea for a podcast, so I'm very happy to be interviewed.
So why don't we start by explaining what you're researching at the moment and go from there?
Yeah, so I work on collider physics, and colliders are just a very simple example I think that we all get. They're just atom smashers. So ATLAS is my main project, and it's an experiment at the Large Hadron Collider, the LHC, which I'm sure almost everyone has heard about. And the LHC basically takes protons and smashes them together as... Firstly, the protons are sped up, not because we want them fast, but we want them very energetic. So we speed them up almost to the speed of light and smash them into each other. And basically what ATLAS, my experiment, does is it just watches what happens when the two protons collide. It's a very small scale process, so we have to use quantum mechanics. And quantum mechanics is not fully deterministic. It doesn't tell us what happens exactly, but it gives us a probability for different things to happen. And most of the time, what happens is the protons just, sometimes they can kind of just deflect each other. That's not particularly interesting, but when they don't just deflect each other, they can cause one of the protons to split up into fragments and the other one to stay integral, and that's also not very interesting. We're actually most interested in the very, very rare processes where both protons are completely obliterated, and then the quantum mechanics, the particle physics of the really small takes over. So what I'm most interested in from coming out of these collisions are Higgs bosons. But the probability to get a Higgs boson in any one of these collisions is about 1 in 10 billion.
Oh, wow.
Yeah. But that's no problem, because what we do is we actually have these collisions between protons every 25 nanoseconds, so 40 million times a second. And yeah, like I said, ATLAS just watches what happens. So that's ATLAS, and I have a kind of second project, like you mentioned already, the Compact Linear Collider. So it's a fantasy project of physicists' dreams, and it would be a project that would be for CERN in the future. And instead of colliding protons and protons, we collide electrons and anti-electrons, or positrons, also at very high speeds, at very high energies. And again, the idea is just to watch what happens in the collisions. And one thing that will happen in the collisions is Higgs bosons, but also a lot of other things. But again, Higgs boson is my main interest. And the reason that I think that would be a very good project for the future of CERN is that you could make very, very precise measurements of the Higgs boson at click, more precise than we can do at the LHC. So it would be a very nice complement to the data we're getting from the LHC.
Amazing. Yeah, that all sounds so interesting. And studies into Higgs boson, where do you think that they'll go in the future? What do you hope to find by studying more about the Higgs boson?
So, the Higgs boson has a long history. So the Higgs boson, the idea of the Higgs boson was first conceived actually here at the University of Edinburgh over 50 years ago by Professor Peter Higgs, who was actually originally a physicist, not a particle physicist, but he worked in condensed matter physics. But he had seen some similarities between the theoretical work in condensed matter physics and the theoretical work in particle physics. And actually, at that time, back in the 60s, people were working out the framework for how we currently describe the way that interactions of particles take place on these tiny scales. And in particular, we didn't have a good way to describe theoretically why some of these fundamental particles have a mass. That the theory worked great if they were all massless, but they're not. And we knew that. We knew that things had a mass. And so he came up with a way to account for their mass theoretically. And as part of that, he predicted that there would be an extra particle, and that he didn't call it the Higgs boson, but slowly it was named after his work, so it was called the Higgs boson. And then fast forward something like 45 years later, this was like the only particle in this now very beautiful complex theory that had been built up over the 60s and 70s and into the 80s. That was the only particle that we hadn't seen was the Higgs boson. So when the Large Hadron Collider was turned on it started first collisions in 2010. That was the main thing that we were like really excited to see if it actually existed. And the reason it hadn't been seen before is that it's in any collision, it's very rare to make a Higgs boson, but the LHC is like supercharged. It does collisions every 25 nanoseconds. The energy of the protons is very high, and it doesn't actually just collide one proton and one proton every 25 nanoseconds. It's bunches of protons. So right now it's about 40 and 40 every 25 nanoseconds. So the chances to see the Higgs boson were much higher. So eventually in 2012, we had enough data and we saw what we wanted to see. So how do you see a Higgs boson? Higgs boson, unfortunately, once you make it, it decays. And it decays in, we don't actually know, but the prediction is about 10 to the minus 22 seconds. So it's gone. You make it and it disappears. So my favourite particle is just gone. But it doesn't disappear into nothing. It decays into other particles that we can see. So one example of this is it can decay into two photons, two particles of light. And the ATLAS experiment is essentially just a huge digital camera, and it can detect the two particles of light, and it can measure their energy, and then where they end up in the detector measures their direction, and so we can get their momentum. And from this information we can trace it back and work out or get an indication of what made those two particles of light. And so we started to see that, as well as just kind of random coincidences, we started to see a little bump in the distribution, and that, as we took more and more data, became more and more obvious. And that's what we used to discover the Higgs boson. So the Higgs boson can decay to two particles of light, but there are lots of other things it can do as well. It can decay to a whole other set of the fundamental particles we know, such as the Z bosons and the W bosons, the bottom quarks, charm quarks, gluons, tau leptons. And what I want to do is just kind of make sure that these predictions are all correct. So actually, one of Peter Higgs's papers from later on in the 60s actually says, oh, well, the Higgs boson will decay into all these things, and here is a prediction for how often, how frequently it's going to decay into each of these things. So that's something that we want to test. The other thing that I'm also particularly interested in at the moment is, so a way I think about it a lot is, we've got Higgs bosons, and there's two things you can think about it. So you can think about how it decays, and we've talked about that, but you also can think about how you make it. So it's a bit more complicated than just smashing the protons together. I mean, the particles inside the protons have to kind of gang up to make the Higgs boson, but they can gang up in different kinds of ways, and you can, for example, make a Higgs boson along with top quarks. And that's what I'm really interested in at the moment, is the interaction between the Higgs boson and the top quarks. Now, the top quark is the heaviest of the quarks, and a Higgs boson just does not have enough mass to decay into top quarks, which is something that could happen. And that's something that, if the Higgs boson was heavier, that's something we think would happen, but it's just not heavy enough. So instead, what we have to do is when we make top quarks and Higgs bosons together. And so that was actually seen, making top quarks and Higgs bosons together, for the first time at ATLAS, and also at another experiment at the LHC CMS last year. So we saw that, which is great, because now we know the top quark and the Higgs boson interact, which is what we thought. But there's more that we can do there. For example, the way the Higgs boson behaves is interesting, and that actually relates to something I did when I was a PhD student about CP violation, whether the Higgs boson respects CP symmetry, which I'll say what it is in a minute, or whether it can flip the CP symmetry. So CP symmetry is very basic symmetry. It's a symmetry between particles and antiparticles, for example, between electrons and anti-electrons or positrons. And the question is, do they behave the same but just kind of opposite? They've got opposite charges to each other. And electrons, as far as we can see, really do. But some particles, for example, the particles made out of quarks, don't respect the CP symmetry. And the question is, well, does the Higgs boson respect the CP symmetry? And that's something that we can try to understand a bit better by looking at how it interacts with the top quarks. So that's kind of my main focus right at the moment.
Yeah, wow, that sounds very exciting.
Yeah, it's, I mean, a lot of it's quite detailed and subtle. It was great when we were looking for the Higgs boson, because there was like a really clear story, and now we have to keep defending why we're keep on doing Higgs boson physics, because they're like, well, you found it, surely aren't you happy? And I'm like, I'm ecstatic, but you know, it's, finding it is one thing, checking that it's really the same thing that Peter Higgs predicted is a whole other thing, and takes loads more data, which is why it takes more time, because we just have to wait with the data.
Yeah, and there's just, like you said, it's kind of the reason the LHC came about was to search for this Higgs boson in the first place, and now that we've found it, there is a lot of questions on, you found it, yay, like, where is it going to go now? So it's really interesting to hear that there's still more research to be done about the Higgs boson, and that there's so many questions still left to be answered about the behavior of it. I kind of want to ask you about looking at these behaviors of the Higgs boson, how it decays, and its interaction with top quarks. What do you hope to find about the Higgs boson that could maybe be related to other areas of physics, or explain the nature of the universe a bit more?
Okay. So sometimes people ask, well, what use is the Higgs boson? And I often say the Higgs boson is of no use whatsoever. And that's because when you make it, it decays in 10 to the minus 22 seconds. And I can't think of anything that you can do in 10 to the minus 22 seconds. So its relation to other areas of physics directly is very small. But in order to even build the LHC, there was a lot of engineering physics that had to be developed and industrialized. And so there was a huge kind of knowledge spin-off in designing and creating and then building all the equipment, all the pieces of the LHC and putting it together. So a lot of the designs were done at CERN and at universities throughout the world, but then they were generally built in industry. So that's one way that the knowledge of these things is transferred over. What I think personally I find more interesting is its connections to what we know about the universe. So I hope you're going to interview an astrophysicist or a cosmologist at some point as well. They probably know much more about this than me. But we do think that shortly after the Big Bang, there would have been lots of Higgs bosons existing inside the kind of mini hot bubbling universe. And perhaps, maybe not the Higgs boson itself, but what we call the Higgs boson field, or the Higgs field we should call it, did influence the way that the universe evolved at early times. But the jury's really still out at that, because it seems it doesn't quite explain the universe the way that it is. But we do need it for particle physics to explain the particles, the patterns of the particles that we see and the patterns of their interactions. I do have one thing we could talk about, which is the fact that I work in a collaboration and it ain't just me. Because I think that's important, just to get over that. It's just not me sitting behind my desk running everything, but it's a huge collaboration.
Well, how do you find working in a collaboration versus working on research alone? What are the benefits of working in the collaboration that you found?
The collaborations I work in are enormous. So CLIC, which is the smaller of them, there's about 200 of us just working, not on designing the accelerator, that's a whole separate team, but we're just working on designing the detector that would look at the collisions and thinking about the physics that you could do. And the Atlas collaboration, which again is just the people that built and operate the detector and analyze the data, not the LHC team, they're separate. Each of our papers has about 2,500 authors. Everybody is on every paper, but that's only about half of the team. There are about another half of the team who are engineers or master's students or computer scientists that don't go on the paper. That's about another 2,500. So there's about 5,000 of us in Atlas. So it's super collaborative. And that I find is really great because it brings together everyone's strengths. So I am really, really bad with being in the lab with a soldering iron and trying to test equipment. I'm just so clumsy that I'm not really good at doing that. But this is great because there are great detector physicists that help us design and collect the data, and then I get to analyze the data and see what comes out the other end. So look for my Higgs bosons and look for my top quarks and things like that. So it pulls to everyone's strengths. So instead of maybe being a master of many topics, I can just focus on the things that I'm really good at. The other thing is we have to be super organized. So we all get roles to do certain tasks. So one of my tasks actually is to check that some of the software that we run when we're collecting the data is working. and if we find any bugs in it, I don't actually correct them myself, but I go off to the person that wrote it and said, look, there's a bug in your piece of software I can see here. Is it important? Do you need to fix it? And they will say, oh yes, it's really super urgent, and they'll fix it. Or they'll say, okay, no, that can wait a couple of months because I've got other stuff that's more urgent, and come back and do that. So I really enjoy working in the collaboration. And it's also, actually, when I was doing my PhD, and I also did that at CERN on a much smaller experiment, it was excellent because you had a choice of role models. So like, it wasn't just your supervisor. There was lots of really great, enthusiastic people that I could work with. So to some extent, I spent a lot of time working with another researcher and not so much with my supervisor during my PhD. And I really enjoyed that because she was really super supportive day to day. And I think for a lot of people, that's one of the attractions of working in experimental particle physics, that you do work as a team and you do work together, and you're not just alone fighting with your own ideas. You've always got someone to talk to and to develop things further with.
Yeah, that sounds amazing. I feel like in physics, and when you're talking about research, there's not a lot so much about the collaborative aspect. Whenever we're talking about like research or theories or ideas, it's very often related to just one person.
Mm-hmm.
So it's nice to have CERN and Atlas as an example of how great a collaborative environment can be and what it can produce. Because
I think also that you might think that some people work on their own. I think everybody has a team. Almost everybody. I think Peter Higgs did really think of the Higgs idea on his own. But I mean, even these days, people that are very theoretical, work with their PhD students, and they might have research assistants as well. And okay, maybe they're working individually on slightly different topics, but they do talk to each other and they do share ideas. So to some extent, I think all work is collaborative, but at Atlas, it's a completely different scale. And sometimes I think we're a bit like an army, because there are roles, there's like a hierarchy of roles and different working groups and things. But the nice thing on Atlas is you can also choose. You can say, well, my speciality is doing software, and you can just mainly do software. And then when it comes to doing looking at the data, I can say, well, I want to look at Higgs bosons, and they could say, okay, like Higgs boson people over this way. But what I think the other thing that's really nice is due to the quantum mechanics. So when we collide the protons together, 1 in 10 billion times makes my Higgs boson, but maybe 1 in a billion times you just make top quarks. And I've got colleagues, friends at other universities that really love top quarks. And so at the same time as we're taking data for me to look at the Higgs boson, we're taking data for them to look at the top quark. And we're taking data for people to look at the way that quantum chromodynamics works, and data for people who are searching to see if there are extra particles that we didn't think about in the first place. So, we're not fighting over who gets to do what. We can all do it at the same time, just because the stochastic random nature of these quantum mechanical collisions, which is great.
Yeah, that sounds brilliant. Sounds like such a nice environment. How did you end up becoming part of this collaborative environment back when you were like in PhD?
Yeah, so this is back in 96 when I was doing the final year of my BSc. So we were the last year that could only do a BSc. And so the next year they had just introduced the MPhys degree. So we were like the last year that didn't have a choice to do MPhys. We all just had to do BSc. And I knew for ages that I was really interested in particle physics, but we never really got many lectures on it. And when finally the particle physics lecture came, and they were at 9 o'clock in the morning, and the lecturer, Professor Ken Peach, was a bit less organised than maybe he really should have been. But the lectures were so interesting, and I remember you could see people falling away, because actually back then you didn't have to pre-choose your courses. You could say at the end of semester, right, actually I want to do the exam in this and I want to do the exam in that. So you could see people falling away. But eventually I was just like, this was so good. I went up to him and said, do you have any PhD places? And he said, he's a big, loud gentleman. I'll see what I can do, Victoria. And he came back a week later and said, I think I've got something. And that was basically it. And I went to work on a project that he was working on called NA48. It's a really unexciting name. It was the 48th experiment at the North Area, NA, at CERN. But we were looking at CP violation in kaons. So kaons are particles made with one strange quark or an anti-strange quark and another quark, an up or a down. And I was just kind of parachuted into this environment. One of the other PhD students from Edinburgh, she was a year above me, brought me in and said, this is Victoria. And I was just completely accepted into the group. Like, okay, Victoria, now you're part of the team. And that was such a nice experience, just to feel already like you were an integral part of the team and that you had something to contribute, even though you were brand new. And I think that's where I first got that, or learned that collaborative environments are what I want to work in, and that can work really well as a way of doing research and educating and supporting researchers working together. And then I was given, tasks to do. Well, why don't you do this? Okay, let's do that. Why don't you do that? And there's always something to ask when you get stuck. And that's how I got into that environment. And I liked it so much, I didn't leave.
That's really nice to hear, especially, just to get into it. And it's so weird how things just kind of fall into place. And like you said, you just went up to your lecture and then you found a field that you really enjoy and the environment that you really love. And it just took asking your professor if there was any PhD slots.
Yeah, so maybe that's some good advice. I don't think you would get such a clear response these days. You'd be told to fill out the form, and they'd explain lots of other extra details. Yeah, that maybe things aren't so straightforward, but they're probably a bit fairer now. I mean, because it was just because I went up and asked, and maybe that's not the best way to select students, but that worked out for me. So that's the other thing that makes me think I'd never really had a huge master plan in being a physics researcher. I feel like I've kind of stumbled from one opportunity to the other, which has been great. But again, I don't always think it's that easy anymore to kind of stumble your way through, but maybe it is.
Yeah, I mean, it's kind of nice to hear that you didn't have a master plan, because I speak to so many students now, they're like, I have no idea what I want to do after university. I'm just going to get through a bachelor's and see where it takes me. So I guess even though it may not be as simple, it's still kind of nice to hear that even professors, they didn't have any sort of plans when they were in our position, and yet they still ended up being amazing lecturers and doing fantastic research. I think it's something that's kind of reassuring to hear almost. So I also wanted to ask you if you had any advice for any students currently, advice on maybe going to research or advice just being an undergraduate student as well?
Any advice? I think my advice would actually be to read around what you find interesting. So don't just stick to exactly what you're being taught. So if there's some, and you don't have to do it for everything, because there are areas of physics I think that we all prefer over others. But just if there's something that you find interesting, maybe go to the library and see if there's another book on it and read that. Or do the first thing that I do for everything as well, is just look up Wikipedia and then see more about that. And I think that's just a way to kind of satisfy your curiosity in different things. The other advice I'd like to give to everyone, but it might be a bit late at this point, is learn a language, because that's the one thing I really regret, that I don't really speak any other language, because I never expected to go off and work abroad. I never expected it would be useful to have a second language, but it so would. So I would always suggest anyone to go and learn a language. But also, if you've got another interest that's outside of physics, I think developing that's also like a super good thing to do. Whether it's it's sport or music or I don't know, producing podcasts or something. I think it's a great thing to have something else that you're good at, because there are always skills that you learn somewhere that are useful in physics research, or not in physics research if you go off and go into some other kind of career. I think they're always useful, and the more good skills you have, I think the better.
That's really great advice. Thank you. It's something that probably people wouldn't think about, like learning a language or developing other skills. You can get so wrapped up in focusing on physics or the subject that you're studying at that moment that these other skills are important. They are going to make you stand out, I guess.
Yeah, I mean, and I know a lot of students have part-time jobs, and I think even the skills that you get doing that, I was only ever seemed to be a waitress, which I hated. But what I learned was, how to be polite and how to be patient, and sometimes the art of small talk, which I feel I'm really bad at. And they're all still really useful skills, being a physicist, because I have to work with people, and obviously being polite and being patient, and sometimes just chatting about the weather, it really helps build relationships with other people, and that just helps the collaborative work. So I think it takes a lot of different skills are useful in doing physics, and I think just trying to do them all to the best of your ability is really useful. Yeah.
And then I also wanted to ask you, so how come particle physics? How did you decide that was the area of physics that you were going to go to?
How come particle physics? I don't really know, honestly. What I do remember is being at school and doing, in chemistry lessons, doing atoms and like the structure of atoms, and I was like, whoa, this is so interesting. And then I remember quite clearly the day I was doing higher physics with my great physics teacher, Mr. Sampson, and I realised that actually all of that stuff wasn't chemistry, that was physics. And that was the exact same day, probably to the second, that I decided I wasn't going to come to university to study chemistry, I was going to come and study physics. So I think I was just always fascinated with the small stuff, which is strange, because the other part I really find interesting is the big stuff, is the astronomy stuff or the cosmology stuff. And I find it so fascinating that looking out into the universe is exploring the same physics that we look at when we look at the very tiny stuff. And I love the idea it's kind of a full circle. And the other thing that I'm slowly developing an interest in is kind of engineering physics. I'm fascinated about the way that people can develop and build machines. And maybe this is from working at CERN, where people develop, build, operate huge machines. Okay, we do it to look at tiny stuff. So I just did a project with some of the senior honours students, so the fourth year students, on the Queensferry Crossing, the new bridge over the Forth, the new Forth Road Bridge. Because when you make something, it's so visceral. I find that so fascinating. I'm never going to become an expert in that, but I have this fascination for kind of big public works projects, wind farms as well, wave power.
Yeah, that's really interesting. Like the fact that you just loved the small stuff, and you're right, like I love the connection between particle physics and how it can relate to research going on in astrophysics. I think it's so cool that just these tiny particles can relate to something so huge, and you'd think they'd be total opposites, but they're actually not. They interlink so beautifully sometimes that it's just fascinating. And even in engineering and making stuff, the way it just all interlinks and the way it can come together so greatly, it's very interesting. I agree.
So the other thing I do often think about, which I think is really important and is perhaps the kind of defining quality of physics, is emergent phenomena. So I mean, I think about electrons and quarks, maybe protons and neutrons, but as soon as you get more complicated than a helium atom, right, so that's 12 quarks and 2 electrons. Particle physics, the way that we describe particle physics, is really not a very good way of describing how an atom works. You need to use atomic physics. Now, yes, it's based on the particle physics, but you really need to do atomic physics to think about how atoms work. And then when you start to put atoms together, you don't think about individual atoms anymore. You start to think about the properties of the kind of bulk system, and then it kind of moves into condensed matter physics. So these kind of crossover points and how different phenomena emerge when you start to put things together, I mean, I think that's really fascinating, and how we think about that and how we describe that. And that's actually why I love working in the School of Physics and Astronomy, because there's all kinds of different physicists here and all working at different length scales and all doing physics, but they're all kind of based on the same approach to the way that you look at the universe and the world around us. And we discover so many different things. And yeah, I like particle physics, but using the same approach of doing experiments, of looking at the data, of seeing what happens, can lead to finding out lots of different things about the universe, which is great. I love physics.
Yeah, such a statement. I love physics. Yeah, that is definitely a viewpoint that I wholeheartedly share. So I wanted to ask you, what's your favourite thing about being a researcher? What makes you want to continue being a researcher?
Oh, what makes me want to continue being a researcher? So, I mean, actually, I don't spend that much time myself anymore doing the research. Now, you might ask me what I mean by that, and what I mean by that is actually analysing the data. And what we do a lot in particle physics is we make histograms and plots and look at correlations and things like that. So I don't get a lot of time these days to actually do the code and look at all of and make that data analysis myself and look at it and try and work out what it means. So a lot of the time it's my students, my PhD students, that do that and then say, well, I've done this and I've done that, and then we talk together about what it means. And I think one of the things that drives me is the hope that I might actually find some time one day to do that myself. But maybe the answer the proper answer, the answer you're after, is that there's still so much more that I want to know. So there's so much more I want to know about the Higgs boson. So one of the reasons I think I've got this kind of fascination with the Higgs boson, I was actually taught by Peter Higgs back in 95 and 96. And it was the year before he retired, so it was the very last classes he was teaching as well. And just this kind of idea we knew that there was this thing called the Higgs boson, but I don't think anyone really knew exactly what it was. But there was just kind of this rumor that we had that he'd invented this particle. And just since then I've thought, well, okay, that's the one I want to find out more about. And I think it's just there's so much more to know, and that's why I want to find out more about physics and help the process of finding out more about it. And okay, even if it's students that actually do the hands-on work, I still get to see those results before most other people. Just me and them have a look at them together. And so also maybe just that fascination of knowing something before everyone else does. Even though as part of a collaboration, I mean, in like 2 days' time, you'll tell the working group that you're working in, and eventually that's put together with all other people's work, and in 6 months' time there'll be a paper, and so everyone else can read about it. But it's there's just more to know, and I want to know more.
Exactly. I feel like with physics there's so many unanswered questions still left to go out there and answer. It's quite a drive to have for a subject, which is why I'm also fascinated with it, and why I'll probably keep on going with it. 'Cause, for example, with the Higgs boson, we found it, but then there's still these other questions that we want to find out more about it, and just keep on going with researching it and finding out more continuously. The last question I want to ask you, do you have an inspirational book or article that you've found just really ignites your passion for physics and that you'd like to share with our listeners?
That's a really good question. And I can't think of anything on the top of my head. This is really, really bad, but actually not what you were looking for, but what I do remember was one thing that probably inspired me as a little kid is the Ladybird books that my dad bought me on mathematics. I remember that one very well, and on it must have been like astronomy. And I think maybe that's what initially got my attention. I don't know actually. What I like to read best are the articles in the kind of physics magazines that we get. So the one that the IOP sends. What's that called? Physics Today? No, it's not.
Physics World?
Physics World.
Yeah.
And CERN produced one that's very similar called the CERN Collider. And those are the ones I actually like to read best. Not for inspiration. Usually I'm not inspired to apply something to my research, but just I'm inspired because they illustrate that there's so much more that we can still know, because this person has focused on in this area and found out this extra stuff that people didn't know 3, 4, 5 years ago. And I think just those kind of things, there's still so much more that I can learn in my field, and they're the kind of things that I find most inspiring to read.
Yeah, no, that's amazing stuff, especially the Ladybird books as a kid. That's a great thing. That initial spark of physics came from Ladybird. That's amazing to hear. Yeah, so thank you so much again for being on this podcast. It's been amazing having you and sharing your research and the story of how you became a lecturer. It's been fantastic. Thank you.
No, you're very welcome.
So thank you for listening to this week's episode of Delving into Academics, and I hope you found it interesting. Please like, review, comment and subscribe wherever you're listening to this. And if you want to find out more about the researcher, I will have their university website page linked in the description. See you in 2 weeks for another episode.